but we'll probably do that in class sometime next week. And then there's also some coding questions in here, conceptual questions about D3 in JavaScript. You will not have to know which function does what in a D3 force-directed layout. That is not important, but you should really have a good understanding of data binding, of what does enter do, what does update do, how do you merge selections, and so on. So these basics of D3. And I like to give a find the bug question. So like I'm asking you, this is the code, what does this render? What would you expect it to render? How do you fix it? Something like that. So you're not going to do like a lot of coding, but you'll have to look at code and find a problem with it and suggest a solution to that. Any questions about that so far?
How big a section of code are you talking about? Like, just
on the scope of this, like the lecture stuff that I did. It's like it fits on a page printed, so it's not a lot of code. It is like a bar chart stuff. If you did your homeworks, and if you know what your homework does, then you should be fine without ever studying for that. Okay, so let's talk about interaction. This is a fun class to teach because we'll see a lot of cool videos. So why do we want to interact with visualization? Well, it turns out that data is big and complex, and one way of dealing with this size and complexity is simply to not show everything at once, but instead to use interaction to reveal details about the data. For example, like you have an overview, you find something that it looks interesting in an overview, and then you explore the details. Or you can also explore some data set with different representations. You could like switch between different visual encodings so that you get a better view of a specific property or can answer a specific question. And the idea here is really that interaction amplifies conditions. So we understand things better if we can touch them and if we can interact with them. And also if we can observe cause and effect. So how would we interact? So there's of course like we use interfaces like mouse and keyboard, and these are the ones that we in this class usually design for, right? But sometimes this isn't really so important anymore. Well, still people use 50% probably of the internet traffic is still, or of the newspapers traffic is still over the desktop computers, but still you get 50% of all users of the New York Times, for example, now access the website with a mobile client. And so that means that they have to really think about what does it mean to interact with their visualizations with touch and with mobile. And so if you look at the progression that they made, they kind of like simplified their charts a lot. So they, in 2013, 2014, they had these very interactive charts, but basically you could only use them on your computer. And if you look at, for example, the election visualizations this year, you will find that all of them actually have, like, show everything in a static way. So you can always see them on your phone. So touch interaction mobile is something that we don't really deal with in this class because we kind of take a little bit of an angle from this like expert analysis side. But it is an important aspect. What about gestures? Who thinks that, like, what could you imagine doing gestures for visualization?
I mean, they have the infrared trackers.
Yeah, and so you think that would be good to use for visualization? Also eye tracking. So for example, there we talked about eye tracking for studying how people like perceive a visualization, but you could also measure the eye gaze and, for example, select an item based on your gaze. Actually, one of my first research projects did that, and it turns out it doesn't really work.
It'd be really confusing.
So for eye tracking, there's this problem that's called Midas touch problem, because your gaze is not voluntarily, right? You cannot steer it. Everything that you look at turns to gold, or everything that you touch turns to gold is the Midas story, and everything that you look at is automatically selected. So there's these problems with these interaction techniques, and there's this one video that I wanted to show with the name I Hate Tom Cruise.
Hi, I'm Alice Kaufman. I'm an interaction researcher, which means that I explore and prototype future uses of technology as a way of understanding the future. And I really, really hate Tom Cruise. I specifically hate Minority Report Tom Cruise. with his perfect haircut and his power stance, chopping at the air to sort of scroll through scenes of crimes that haven't happened yet, because it has conditioned us to expect that the future of gesture interfaces is going to look dramatic. You know, all the gesture tech we're building, the Leaps, the Connects, the Mayos, they all demand these highly visible gestures that are distracting us from a more pedestrian, less cinematic future that is definitely more usable than this. I mean, every time I see this scene, I think, Tom, you're standing 2 feet away from the screen. Why don't you touch it? He's replaced direct manipulation, which our hands are really good at, with this kind of elaborate sign language, which our hands are really bad at. It's as if I said, like, it's the difference between solving a Rubik's Cube and explaining to somebody how to solve it by pointing. And the thing is, our hands are very coordinated. I mean, you can be walking down the street and pick up a penny without breaking your stride. But unless you're a mime or a dancer, you're gonna have a really hard time pointing at the same spot in space twice in a row. And anybody who's ever used a Wiimote knows it's really hard to point precisely. But I think there's a feeling among people that somehow getting rid of a controller makes an interaction feel more natural. And people become so obsessed with this idea of getting rid of the mouse and replacing it with gestures that they've actually forgotten how we use our hands. Because most of the time, we're not gesturing. In fact, 90% of gestures occur when we're speaking. And studies have shown that all of those gestures, almost to the last one, are for the benefit of the speaker. They help the speaker keep track of what he is saying. They convey no useful information to the audience. Now, I'm not saying that we can't use gestures and interfaces. What I'm saying is that we've got to pay attention to what their unique characteristics are. They're fast, they're silent, they can be performed at sort of any variety of distances, and most importantly, they have this kind of inherent directionality. So at least in theory, you could use gestures as this kind of meta-unifying input across a series of devices. And what I mean by this is, for instance, if I point at my stereo and it turns on, and then I point at it and it turns off, and then I point at my TV and it turns on, and I point at my TV and it turns off, I've actually established a common language that both of these devices understand. And I can use this language as a way to connect them in a very intuitive way. So, for instance, if I point at both my TV and my stereo, if the TV is on, it pipes the sound to the stereo. Or if the stereo is on, it actually pipes the music video of the song that was playing or the album art. This all sort of presumes that gestures are these explicit and very deliberate motions. And I think actually the real magic happens when the applications start to pay attention to what we do with our bodies normally, what we do with our hands normally. Because once machines can interpret our normal motions, they can find some insight into our intentions. And machines that understand intentions can actually start to help us. So for instance, if I'm sitting on my couch watching my TV, and I pick up my phone, maybe I'm one swipe away from the remote control app, or from the Netflix app. Now, if I happen to pick up my phone while I'm looking at my stereo, that same swipe might take me to my music playlist. Similarly, you can imagine a situation where picking up the car keys from the table as I'm walking outside takes the last 5 addresses that I've looked up and just sends them to the car's nav system, and grabs that podcast that I was halfway through, and sort of cues it all up on the car radio. And ultimately, I think that this is what the Minority Report interface is getting at. I don't think anybody, not even Tom Cruise, really wants a Dance Dance Revolution version of Photoshop. I think the goal here is really to help people to establish physical mastery over a digital world that's becoming increasingly complicated and hard to understand. And so I think in order to be commercially viable, these gesture interfaces can't require us to learn a new abstract physical language. They're just going to have to learn to find meaning in the movements that we already make.
So yeah, it's a kind of a side trip into user interfaces, but these gestures, eye movement, and so on, for visualization and for the purpose of this class, they are definitely tricky to use, and you should really not overuse them if you ever get into the situation of having the opportunity. So the rest of this lecture I will talk about types of interaction for single views or for multiple views. We'll look at change over time, at navigation, how do we navigate like a space, at semantic zooming, at filtering and querying, and focusing context. And then we'll look at multiple views for selection, where we do details on demand, for linking and brushing. I highlight something in one view, it is also highlighted in the other view. This will be a big part of the next homework, and on adapting representations. So we will not get to all of this. It's not necessarily the next lecture, but it's going to be sometime soon. Okay, change over time and transition. So how can we interact with time? So we had this principle of eyes over memory, if you remember it correctly. So instead of doing animations, for example, we could actually show you all the data. But we could also, there's also good interaction interfaces to show change over time. So this was another project in the visualization class I taught. And so this shows you the growth of a nation, how the railroads changed the face of America. And so here I can basically scroll through the years, and I can see immediately how that has changed. So that was a student project. And so these are like the filled in states are the states that are actually part of the USA. And then you see that here the Transcontinental Railroad was completed with the Golden Spike in Utah. That kind of triggered this growth in the West that we observe here. So here we have this this here represents a timeline, and that is kind of an intuitive way of interacting with that. So here we could have done something better. We could have had scales here. We could have, or at least if I hover over here, I could see where I'm at right now, or it could be dynamic. But yeah, this was a student project, and generally this is a way of interacting with time series. Change over time doesn't really have to be literal. You can also change stuff as you go, as part of an analysis process. So let me show you this tool. I'll come back to it eventually, I guess, but this is a tool for visualizing rankings that colleagues and I have developed. So this is like a university data set. You can see university ranking, US News and World data set from 2014. These are the top 40 ranked universities, and we can scroll down and see more. But then somebody has defined here the 40% of the score is given to academic reputation. 10% is given to employer reputation. 20% is given to faculty-student ratio. So an editor has made a decision about what is important, but you maybe have a different opinion. You say academic reputation is less important for you than faculty-student ratio. So you could simply change that here and modify that. And so here we interact and basically change the data dynamically. So next I want to talk a little bit about transitions. Why do we want to do transitions? Well, different representations support different tasks, and then if I have two different representations and I want to switch between them, I can do a hard switch, but I can also do an animated transition. And with D3, for example, this is easy and nice to do. So we can, for example, sort, change ordering. In the homework that you're currently working on, it would have been nice to add transitions. If we resort them, then all the rows shuffle around. It turns out, because we made the simple approach of using a table, an HTML table, instead of rendering everything with SVGs, this is hard to do. So we didn't ask you to do it, but it would have been a nice idea. So here is an example of changing between different representations. So this is genomic data. It's not really important what the meaning of this is. But so here we have one view. Then we change the spacing here. This is basically two different spacings that have different meanings. Then we can make this more abstract representation out of it. We can switch into a 3D representation. We can switch into another projection, essentially, into 3D. Or we can turn this over and look at this other aspect of the data from the top. So here we have switched through many different states and we have had these continuous transitions, so it was easy to keep track of what is going on. Here's another example of some of my own work. So here we're looking at movie genres and how they overlap. So we have action movies, adventure movies, children's movies, comedies, and so on. And then we have attributes about those. So you can see, for example, that action movies, there's 283 action movies that are only action movies and don't have another genre in this data set. There's more than 1,000 comedies that don't have another genre in this data set. So by now this is sorted based on the sets here, but I could also sort it by the size of these intersections. And so now this does this all very smoothly and very dynamically. I can sort by a statistical measure of how surprising such an intersection is. And you can see that this is all, like everything here works smooth and you can keep track of it. One problem with that though is that it starts to get a little bit like useless when you have a lot of data. So here we actually have so much data that we turned off the sorting. Let me remove one again. So basically here I'm changing so much that the sorting is kind of a meaningless operation. So there's limits to how much you can actually do with transitions, because here there's just so much going on off screen that you can't really keep track of what is going on anymore. So the idea is that transitions make it possible for users to track what's going on, to see where a specific element, for example, is across states. Here's a couple of other examples. This is a video that I showed in the very first class for focus and context technique in a tree visualization. So here you represent the hierarchy, and then by interacting with any of the segments, you see this popping out and expanding. So you have a really good understanding of the relationship of this overview to the detailed view outside. So this is a pretty complicated visualization, but I think it still works pretty good well. Here is a D3-based implementation for assumable sunburst. And I think this one doesn't really quite work that well, because there's so much going on, and the animation is pretty complex. And we kind of lose the context a bit here. So you can see that it's pretty subtle to design these interactions, right? Here is like a transition between stacked and grouped bars. Again, that is a little bit tricky to see what is going on. But people actually have studied this in detail. And so this is a video by Jeff Hare, who is also like one of the co-creators of D3, where he explains
when analyzing or presenting information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentages, transition to a scatter plot to look for correlations between two variables, or drill down by breaking up the data by categories. Animation is one promising approach for facilitating perception of changes when transitioning between data graphics. Using design guidelines motivated by research of human perception, we have developed Dynaviz, a system supporting animated transitions for statistical data graphics. Dynaviz provides animations for a number of different transition types, including changes of perspective, filtering operations, and viewing changes of data over time. In some cases, changes of value require changing the axis scales. Here we show sorting operation. Animating everything at once can result in items occluding each other. By slightly staggering the movement of each of the bars, Dynaviz makes the sort easier to follow. Here, a bar chart becomes a radial donut chart. By growing the wedges to take up the whole circle, we form a pie chart. We can also perform drill down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a grouped bar chart. Of course, we can always reverse the transitions to return to the view we started with. We might want to compare different variables in a scatter plot to look for correlations. Here, we keep the y-axis values the same as the bar chart, but use the x-axis to show a new variable. Animation is also helpful for showing transformations to the data. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the transform. Visual encoding such as shape, color, and size can be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran 2 controlled experiments. The first experiment asked users to follow 2 targets across an animated transition and click their final positions. To better test how animation affects memory, we masked the display after the transition by turning it black. We compared static transitions, direct transitions in which all items animate at once, and staged animations where movements were split up over time. Our results found significant benefits for animation and found that staged animations, which split up movements through staggering or separate stages, consistently improved accuracy.
Okay, so let's think for a second about this experiment. Who has like an issue with what he's saying and what he's doing here? Or any limitations that you can think of? So these charts, did they look complicated to you? Did they look like real life examples? Do you think this will generalize to more complicated charts?
It's on the internet, so it's got to be true.
Oh, this is actually a research paper, so it's really got to be true. So yeah, my point here is this is definitely correct, but I don't know how well that really works if it gets more complex. And I also find it a little bit unfair to, like, if you looked closely, the static transitions, they basically really had to read the data value. There was no other option to do. And then here he says that staged animations was consistently better than animation, but if you look at the chart, it was really not much. And sometimes the error bars actually overlap, so this is kind of like a brave claim generally. He makes an exception later that this is not true for this particular one. So, yeah, you always have to like read a study or and see a study with like thinking about the limitations of this study and how generally it is applicable, because I'm sure it tested the right thing, but how generalizable are these results? So changes generally can be hard to track, and if you ever do these, like if you ever find yourself doing a lot of transitions, think about this eyes over memory principle. Instead of like maybe there's a way for you to show all of the data in all of the states, and then you can actually compare them on one screen instead of having a transition between them. I'm not saying you should never transition, it's actually very powerful, but you should always evaluate the question, could I do this with like an additional chart, for example, in a better way? Okay, for navigation is also, of course, like we need to interact with complex, whenever, for example, we look at a globe, we might want to zoom in, or whenever we look at like a 3D image, we might pan and move around, we might want to rotate. So I'm just going to show you one example of a 3D visualization. This is actually also done in the browser, and I can zoom in, I can see this path in the brain, and then I can slice, like you navigate through these slices. So here interaction, especially in the 3D context, is really important. So this only interaction here lets you see all of the data nicely. And in 3D specifically, you get these additional these additional depth clues if you start to interact. I need to close this because it's going to fry my computer. And then all of you have seen like the Google World example. So like this is a conceptual diagram, and it was developed, or the conceptual approach in the 90s, how we can see navigation, zooming and panning. So we have this space scale diagram. So we have this viewing window, and we essentially either move it away or towards a target, and therefore we see either like when we frame it such that the whole object fits, we see all of it, and then once we are like at the level above, where we cannot actually see all of the objects anymore, we can do these zoom and pan operations. So this is like a paper if you ever find yourself in this situation to want to look up the theory of zooming and panning. This is the paper that you want to look at. Here is a nice visualization where we do some zoom and pan for non-spatial data. So this is like this big chart of all of the history of rock, and so you can walk through this by zooming and panning, and you can zoom out and in and so on. So like this is a big image essentially, and you can navigate that. I also want to say a little bit about scrollytelling. You might have encountered that in the past. So this is really an interesting development for storytelling. So there's a couple of different ways of telling a story, right? You could have multiple views and simply scroll towards them, or you could have like stepper interfaces. You probably remember that when we looked at New York Times, the many ways to slice Obama's budget, there were these buttons that you could click, and that would essentially trigger a transition. And so some research has shown that people don't really interact much with these steppers, and so people have tried to develop alternatives to that, and one of the alternatives is scrollytelling. And so scrollytelling is kind of like, some people like it, some people dislike it. It has some kind of disadvantages. It is cool, people like it, like your users will like it, but you have to worry a little bit about continuous scrolling versus discrete states. So sometimes you want to transition between discrete states. Maybe a continuous operation is not the most intuitive here. Also, if you had these buttons and if you have them labeled nicely, you can make discrete jumps. You can say, okay, I want to go to this particular instance. So you have direct access to any of these views. And sometimes people can actually design scrollytelling interfaces to behave pretty unexpectedly. So if you want to read a rant about scrollytelling, you can go to this blog post here. But I'm going to show you a couple of examples of scrollytelling where scrolling is used not in the way that you would usually do it. So this is how the US and the OPEC drive oil prices. So we have this scatter plot where we have oil prices on the y-axis and the oil production in the world on the x-axis. And then we have different years, and the progression of time is indicated here by connecting arrows. So 1996, 97, 98, 99, and so on. And so then we can look at different aspects here, and we get this story. Like we essentially scroll away the text here, and then it essentially breaks this up from yearly to monthly by scrolling. And so this is like an operation that is not necessarily super intuitive, but of course it is pretty nicely done and pretty well implemented. And so then you can keep scrolling. There's different text boxes, different highlights, different features, and we have these nice transitions, and the story is told. But it's probably not a super easy data set to visualize, but it is also tricky to follow the story to some degree. Here is another example, which one of you actually sent in, Siddhartha. And so this is a pretty good example for scrollytelling. It's about what's warming your world. So we have a mix between animation and scrollytelling. So here, basically, what happens here is that this visualization shows us different, what could be causing climate change. And so we investigate each of those compared to the observed trend. And so it's separated first. We can see it doesn't look like to be affected by volcanoes. Or in this case, we actually have this juxtaposition of all of the three effects. So we have an eyes over memory effect. So is it deforestation and so on, and then of course we end up with greenhouse gases and see that it is actually greenhouse gases that correlate best with the trend of climate, temperature rise. So would you need scrollytelling here? I don't know. It is not necessarily, not strictly speaking necessary. I could use buttons. But yeah, it is a design option that you have. Another interaction technique is semantic zooming, and there's another video that I wanted to show you.
Hello, my name is Adam Barlow. I'm a program manager on the Windows Developer Experience team. Today I would like to introduce you to the semantic zoom control, which is included as part of the Windows library for JavaScript. Semantic zoom is a control used by apps in Windows 8 for displaying large sets of content in a truly user-friendly format. Semantic zoom is unique in that it provides an easy-to-navigate, touch-optimized view of the data you present to users. In designing Windows 8, we wanted to ensure users wouldn't have to pan tediously through large sets of content with touch. Semantic zoom is our solution to this problem. It gives users the capability of quickly jumping to sections of the view and greatly reduces some of the pain points traditionally associated with large collections. As you can see here, semantic zoom allows the user to quickly jump to any given location in the view, in this case, the last group of my start screen. Not only is semantic zoom a great navigation mechanism, but it also allows you to communicate a higher level of organization to your data, using the zoomed out or semantic view. For example, in the People app, you can zoom out. Here you will see a higher level abstraction of the data in terms of letters of the alphabet. This is extremely powerful and can be used to communicate important information to the users of your application. For instance, you could use the cell spanning functionality of the WinJS list view to demonstrate the relative sizes of your groups. Although semantic zoom is easily performed with touch using the pinch and stretch gestures, it also works well with mouse and keyboard, ensuring that regardless of input mechanism, your users will have access to the important benefits of.
So I'm not going to show the rest of this video, but yeah, what semantic zooming is really about is that you see an object on your screen, and then as you zoom in, it gets enriched in some way, so you get additional information about this object. So more detail becomes available as a specific part of your view becomes gets more space assigned in the user interface. And so what you should strive for if you build a semantic zoom interface, that it is meaningful at all of the abstraction levels that you have. So we had in this phone book example, we had the letters, and then if you zoomed into one of the letters, it dynamically transitioned into individual people. Here's another example from
LiveRack,
a research
interactive
example.
visual exploration of system management time series data. We show LiveRack, a visualization system for viewing large quantities of time series data in the domain of system management. Monitored devices are represented by rows. This label shows aggregate information about a group, NFS, with 4 devices. Columns show one or many parameters collected from the devices. This column shows CPU usage. In the current overview, each cell is a small colored block. In these 4 cells, green means CPU utilization is above 35%. As I make the cells larger, labels for the individual devices become visible. Also, when the cells get big enough, the server is queried for more data, and then the representation changes from blocks to spark lines. Making a cell even bigger results in semantic zooming to show a more detailed line graph. We can see the current time range by looking at the time boxes to the bottom left and bottom right of the data area. The blue lines show progressive search results.
So the rest of this is not so important, but here the idea really is that you have a color coding that gives you a rough overview, and if you want to learn more about one of the cells, you can zoom in and the visualization will adapt. And in this case, like either showing spark lines as above here, where you get an idea of the trend, or actually showing detailed charts with scales and labels where you can actually read the exact data points. So next I would like to do a design critique. It's this one. You can go to the instructions here or directly to the website. Maybe I have not printed enough here. Yeah, no. Well, you can, if you go on your computer, you can go to this URL. Some of the printer didn't print enough.
Can you put up the Google URL?
Oh yeah, that's right. What's that? Yes.
I'm still getting my bearings. Okay, so okay, yeah, I've got musicians. So yeah, one of the things that I just kind of noticed is color. Like, at first I thought color corresponded to time period, but I don't think it does. I think it corresponds. Does it correspond to style or something? Genre?
Maybe in the legend it doesn't say anything color.
Yeah, it doesn't say anywhere. So maybe it's because I originally thought it was like time period, but I think it's actually genre or something.
Yeah, because even with the timeline, there are more leaves on the side.
So maybe color is just based on the clustering because it's about it's a similarity
Yeah.
with word.
I like the idea that they have to show the relationship with the arrow.
By the arrow thing?
That what?
By the arrow thing?
Yeah, but I think it would be better if you could hover over the arrow and then see the name, because it overlaps with yours.
Yeah, that's one of the things I noticed. Like, look at, like, this is kind of silly about the hover feature, because the cursor includes the label.
Oh,
And so, like, especially something like this, you can't
yeah, that's
see what
true.
it says. So it'd be better if it was, like, above it or something.
And then in this view, there's some that are just covered up in the camera.
Ah,
So you can only,
so, like, what if we did
for me, it'd be helpful if I could hover over the arrow and then see the name. Like down here instead of all of the names. But then that would be like a lot of arrows just pointing at me. No, so these are,
Because, yeah, these people influenced the Beatles. So
Yeah, that's
they were
what I
before
thought.
the Beatles. And the Beatles, I guess these people were still producing music by the time the Beatles came out.
oh, I didn't notice that. I was like looking at the bottom. Mm-hmm.
So it's kind of a goofy little trick. Okay, so color is one of the things you feel is
Well, yeah, because it just doesn't make any sense. But you would need it. You can set them
okay.
all.
So yeah, because
Okay, so what is the data that we have here?
the biggest red. It's not like
Musicians?
with all reds.
And philosophers. So some like artists essentially. And what's the data that the visualization encodes?
Influence.
Influence, yes. Who has influenced whom and who was influenced by whom? How is that revealed? Yeah, exactly. Edges, but only through interaction. So I actually, like, this chart is basically completely useless unless I use interaction with it, right? Because there's nothing that I can read from it without interacting with it. So if I hover over, I get the label, and if I click, I see these edges. How are these dots positioned?
I'm not sure.
This is a similarity map.
Yeah, so this is based on similarity. So this is like a multi-dimensional projection where the author has essentially analyzed how similar are two different objects to each other in a high-dimensional space, and then he has projected it down to a two-dimensional space. And so if you look closely down here, you have like the Sinatra and Armstrong, like the early like 50s, 60s music, jazz kind of music, whereas up here we have things like Kraftwerk, which is not really strictly related to Sinatra, for example. Okay, how is color used? Yeah, redundant for similarity. And what else? What else is encoded here?
The size of the size of this.
What does the size mean? Okay, yeah, that's right. So how do you think could one acquire this kind of data? How could you process this? Do you think that there is something out there that says all of those, like a data set out there that has all of these parameters?
Wikipedia pages.
Yeah, Wikipedia pages would be a good way, but what would you have to do? And then look at what. So if you have the Wikipedia article of the Beatles, how do you know who they influenced? Yeah, so you could look at links. You could look at links to which other artists are they linked. But you also have to be a little bit smarter, I guess, because you have to distinguish between influenced and influenced by. So there's maybe some categorization on Wikipedia. I think this particular data set was extracted from this graph database that is online.
Well, if you just look at the years of the content that you are extracting, I think you can, like anything that comes before an artist.
But that assumes that everybody after somebody is influenced by them, right? And that might be true for the Beatles, but I don't know whether that is true. Like let's look at some of the, like these guys.
Well, I guess it would make sense to look at it on the timeline and see if there are any edges going back.
Yeah, so okay, that's a good point. Let's switch to the timeline. So I have like, there's two different views. I don't know whether everybody has found that, but there's this similarity map, and then there's this timeline view. And so let's take a look at whether, like for example, this band here has influenced everyone in the future. No. So just using time is probably not a good approach. And so what you would guess is that people that are very significant have influenced a lot of other people, but then again, here is another like dot, and the Rolling Stones seem not to have been influenced by the Beatles according to this. I don't believe that. I would guess they have influenced each other. But anyways, in this data, it's shown like that. So what is interesting about this part, about this chart? Anything peculiar that you notice here?
Non-linear scale.
Yeah. What do you think that is?
Density of bands, I couldn't really tell in the
Yeah.
paper form.
No, but I guess it is really density of bands, right? Because you have this explosion of music in 60s and 70s, so you need extra space for that. But then there's less between 50 and 60. So yeah, here they use a nonlinear scale, and if you ever deal with historical data, for example about historical figures, you will find that of course our record about them is much denser in recent years, and like if you go back 1,000 years, then you have a lot less people per year, so you have to think a little bit about your scales. Any comments on this chart? Personal preferences? Did you like it?
Just a few little things that make this more difficult for me to navigate. Sometimes when I hover over the little circles, my mouse pointer obfuscates the text.
Okay.
And then another thing too is just some of the circles are really small, so it'd be nice to be able to zoom in
Yes.
on a particular section and like compare the smaller circles.
That's true.
I think the display real estate is not really used efficiently. You have much less space associated with the circles than when you look at the edges. They occupy a larger sort of space on the screen. I think that could certainly be improved to make the data more clear.
Yeah. I guess it is tough to draw so many edges, but for the less popular cases, that is definitely true.
I also think you don't necessarily need to have so many edges in a sense, because you have two categories. You're either influenced by something or you're influencing something. And you can just categorize them.
So what you say is you could, instead of showing edges, you could show something, like use another visual encoding.
Like the simplest example is just arranging the circles and putting a border around them. So this category, they've been influenced by, and this category, they are influencing that person, and they can share common.
Yeah, okay. And so, could you, what would be the advantage of that?
I think it's much more clear to just focus on the bands themselves, because the data is so defined, you don't really have to pay much attention to the nature of the edges that go from one node to another.
Yeah.
You already know how they're being presented in a sense.
So you're suggesting basically that we use an implicit encoding by something like color instead of the edges. Does everybody agree that that would be a better choice? You can say no.
I think we can still keep the edges, and whenever we choose someone, just rearrange them so we can see the influence bias on the left side and the arrows.
Yeah, that could be a good approach. So I think that both of these ideas are actually pretty good. I think the edges have one advantage. They're quite easily discoverable, so you kind of really understand quickly what they mean. But you're right that they produce quite a lot of clutter. And I think they actually are even worse in the similarity map. So here, if you click on the Beatles, it is basically one big mess.
Yeah.
Me or him?
You.
So one other suggestion that I have was that when we focus on a specific node, anything that's unrelated is still occupying space. and we could easily just expand, especially on the timeline. If you're looking at something specific, there's a lot of nodes that are going to be dimmed and faded out, so maybe we could...
so you could zoom in, you mean like if I have this node
we
here?
could just automatically fit the data to our space, because our scale eventually is non-linear, so
Yeah.
we're not really modifying anything in terms of the axis.
Yeah, this is definitely a possibility. What do you think would be the disadvantage of doing that?
Context.
I
I'd
guess,
lose
yeah.
context.
Yeah, and you get a lot of movement, I guess, in your chart.
Right.
It like you kind of destroy your spatial memory every time you click on something because it's going to move around a lot. You still have relative spatial memory, but like you know that, for example, when you work with this, there's a couple of like older bands that are on the very left.
So would this be an example of like, because we've talked about like sometimes you have so many edges, it's a complexity issue. Will this be an example where it might be useful to have an additional view that would come up when you select it? Like in addition, that would maybe sort things differently, like we're talking about, like sort the influencers by the influences?
Yeah, I think that is a good idea. Like if you really want to focus on influencing versus influences, you could rearrange the chart based on that. In this case, this person has chosen to use edges, but there's other ways like adding a color to that, or adding a glyph, or rearranging using position to encode that. There's a couple of cases here that were actually like the band is younger than the band they were influenced by. How does that happen? Like here we see Charles influences Barry.
Well, I think they just using the same
Yeah.
time period.
So this chart misses what? Like for compare Beatles to Rolling Stones. What does the time show?
Oh, the birth, is it the birth of the artist? Or is it the
The-
publication of the music?
It's probably like the formation of the band, or like this first album or something like that.
Yeah, and so there's no context for the
Yeah.
span of
There's no
production
context
time.
for the span of a career, yeah. So the Rolling Stones, if you look at that, they actually they influence quite a bit of people that are like that were founded before them. So we have no idea, for example, from this chart that the Rolling Stones are still active and the Beatles haven't been in 30 years. So that's something that we don't see in this chart. But it would be tricky to show that here, right? Because then we couldn't plot all of that on the same axis. But it would be interesting to try and to think about how you could do that. So any like personal opinions about this chart?
Is there any reason why the first line is darker than the rest of them?
Other than it being a round number, I don't know. Probably.
Change the data stat, you can see more changes of painters or those outputs.
Oh, yeah, here we see.
what?
Yeah, the century marks are more pronounced. And here we see this nonlinear scaling quite a lot. So this is communicating by these like additional lines.
You know, that, you already commented on this, but I actually think that that could be very interesting because the production career of the artist is a very profound variable in this sort of thing. And so I'm kind of envisioning some kind of like overlapping bars on a timeline representing that. And I think that is a very interesting part of the context for
Yeah.
this analysis.
Yeah, I agree.
That probably would be a different view though.
You have to do something different, yeah. You couldn't do this on this timeline, but you could do it in a table layout, for example. But it's not going to be as compact because you need more space to do that. Okay, so who likes this chart or who dislikes it?
I definitely like a lot about it. You get to explore it. You get to, it's all eyes over memory. We talked about that a lot today too. And I do like the fact that the lines and the edges are there because it does sort of look back. You can look back in time. You can look forward in time. It's a little more challenging in the spatial thing. But
Yeah.
in the timeline, I think it really works quite well.
Any other opinions?
Actually, I don't like it very much because
when I first look at the graph, I don't get too much information. I just know they're different, but for example, what's the meaning of different color? I only know they're different, but I have no idea what green means, what red means, what blue means.
So yeah, you're getting at a good point. You had very different opinions, and I think that basically what you're saying is it is hard to discover, right? But what you're saying is it's great to explore. So I think this is like a very classical example of a chart that initially tells you nothing, and then once you start interacting with it and digging into it, you see the little clever decisions made, and you see the little facts. So this is a kind of a different visualization. It's more, and this is also like Marianne's design philosophy. He's a researcher who cares about like informal information exploration. Like he's coined this term of the information flaneur, this person that doesn't have a goal. He doesn't need to learn something now to make a decision, but he just wants to explore and enjoy data. And so these, like, I think I'll show you a couple of other pieces of his work in the rest of the course. His work is often like not immediately obvious, but then like invites you to explore and play with it and be engaged with it. So I can get lost in the thing and just look at the data and play with it. I really enjoy it, but it doesn't really communicate something like a hard fact at the very beginning and very quickly. Okay, anybody else want to say something? Yeah.
I have a question. Is there any good way to find the best ratio, for example, in this case, best ratio of the radius of the circles to the whole graph? Because it seems for some of the circles they're really small and...
Yeah. You can try to find measures of like how much occlusion are you willing to have, and how would you, and how would you space them out and so on, so you can find like an optimization for that. But this is like a problem that is kind of related to binning in histograms. It's like finding automatic bin sizes in histograms is not trivial, so there's a couple of rules of thumb, but then you either oversample or undersample. So often it's more intuitive to simply try and play with it, and this is where interaction can come in, yeah.
This is kind of a low-level thing maybe, but on the similarity map, and I hope no one's already said this, but this is something that bothered me, is that like go hover over a tiny circle. Yeah, so see the cursor occludes the name.
Yeah,
and like it seems like that's probably typical that a cursor would be below the object that you're hovering, and so you might want to have labels above the object or something.
That's a good detailed comment too. Yep. Okay, good. Who used the like anybody like learn anything about musicians or philosophers or?
My favorite part of the whole thing is that David Bowie's up on the top by himself.
Yeah. So yeah, he is dissimilar. Cool. So let's keep going. So what is focus in context? Focus in context is the idea of looking at one element in detail while still having like an idea of what the rest looks like. If you think of your homework, you have a focus in context interface. You have all the countries that played in the World Cup, and then you can select one to focus on and reveal more data from it. So you can essentially show contextual information. Focus in context is a synthesis of visual encoding and interaction. So we visualize stuff once you have clicked on it. So here the interaction is really critical. The user selects a region of interest, which is your focus. That would be the country that you look at in your homework. And then the interface shows us the context for this particular country. And there's a couple of different ways to achieve focus in context. So we can use it through aggregation, through reduction, or through layering. So these are these different things. And so this is elite data. I never know how to pronounce this. But essentially you have like an overview here, and then you pop something out. And this is essentially what you're doing in the homework. You're not popping it out to the right, but you're kind of moving the rest of it down. And then we could also do superimposition. So if we have two different charts and we want to show the focus and the context of that, we could plot that on the same chart if it has the same scales. Or we could distort the geometry. So if I were to look at the map of the world and I wanted to focus in on Paris, I could simply say, okay, show me Paris in big and distort everything around it. And so we'll look at these properties for a second. Elision is to focus an item shown in detail. So if you, like me, and haven't known this word, if you're maybe not native, yeah, so it's an omission of a passage in a book, speech, or film, the process of joining together emerging things, especially abstract ideas.
Just for the record, I am a native speaker. Didn't have a clue what that meant.
Yeah, that's why I put the dictionary definition in here. So the classical example is these tree layouts, where you can, you have a hierarchy and then you can dynamically expand the elements that are deeper in the hierarchy. So as you can see from the interface, this is an older technique. So this is an important concept. And I had this on the test last time, I'm not going to give it this time, but nobody got it right, or basically nobody, so I did something wrong explaining it, I'm going to try better. Degree of interest function is something like really a fundamental concept for visualization. Degree of interest function has two different terms. What you care for is if you have a big data set and you cannot show everything at once, right? You have to define which of the nodes in a tree, for example, do I want to show, or which elements in a table do I want to show. And so the degree of interest function has these two terms, which are called the a priori interest and a distance function. And so the a priori interest is something that is inherent in the data. So if you look at a graph, for example, if you could say the a priori interest of a graph depends on how many neighbors it has. So you have some kind of the degree of a graph of a node tells you, okay, this node is important for the network. But if, for example, leaf has only one connection, then you might say, okay, it's probably not very important. But this could be anything, right? You could have a graph that is not connected, but you could know more about this particular node. So this is maybe a super important actor or politician or whatever. Then this a priori interest for this particular person could be right. Let me see whether I have a graph. And then we also have a distance function. And this is where interaction comes in. So let's say I have a tree like this, and because of my a priori interest, I may not actually show these 4 nodes here. So I may not actually show these 4 nodes here. So this is the overview that I see first. So we have a high a priori interest in this particular node because it's the root. So everything originates from that node. And they also have children, so they're also considered important. But now, when I click on something, for example, when I interact with this node here, I kind of set this distance function. And now what this means is that the system should be aware of that I am currently interested in this element, and then re-add those 2 nodes so that you have a tree like this. So we have the distance function here essentially has defined these 2 nodes here. They are not important if we didn't click here, but since I'm currently interested, I've shown interest in this particular item, it should reveal that. And so the tree is the simplest example here, but you can actually use this for so many different techniques, and this is such a fundamental idea of these relationships of an a priori interest and for a degree of interest. You'll see other examples in a second. So the classical example is this degree of interest tree. So here's a little video of that. And so you will see that this is it's not gonna hide everything, but it is kind of when you drill down, it reduces the items. For example, I've drilled down into one particular branch, but it still keeps this category visual arts here, but hides the rest of it. So this is like this dynamic idea of adjusting the degree of interest based on the a priori interest and on the distance function to the current selection. Okay, and so this could be like applicable for anything, right? This is not like really not limited to a tree or to a graph. It's easiest to imagine in a tree or a graph, but you could make this happen in a table or in like using bar charts or whatever. Good. So let's call it a day, and I'll talk about superimposition next time.